Have you ever really thought about how we manage to capture something as wild and powerful as lightning and then somehow cram it into your pocket? Well, that's kind of what we're diving into today. We're going to explore the fundamental ideas that make it all possible, from storing energy to getting it to flow. Let's learn how to bottle lightning.
It sounds like a weird riddle, doesn't it? I mean, a massive, chaotic storm cloud and the sleek little battery inside your phone. But the answer is actually pretty cool. They both work on the exact same principle of storing electrical energy. It's just that one does it a little, tidier than the other.
Okay, so this brings us to our first key player, the capacitor. The easiest way to think of it is like a tiny, tiny battery, but one that's built for speed. Its whole job is to hold on to a charge and then release it in a split second. It's really the unsung hero in so many of the electronics we use every day.
And at its heart, a capacitor is incredibly simple. You can literally think of it as an electricity sandwich. Seriously, you've got two metal plates, and in between them, there's a little insulating gap. You put a positive charge on one plate, a negative one on the other, and boom, you've created stored energy, just sitting there, waiting to be unleashed.
So how do we know how much charge one of these things can actually hold? Well, physics gives us this beautiful, simple little recipe. The capacitance, that's the C, is all about the area of the plates, which is A, divided by the distance between them, D. This little formula is the actual blueprint for building a better storage tank for electricity.
Let's just break that formula down into plain English. If you want to build a capacitor that can store more energy, you've really only got two main options. One, you can make the plates bigger, that's increasing A, or two, you can scoot those plates closer together, decreasing the distance D. It's this really elegant trade-off between size and how close things are.
But what if you need to store a lot of energy, but you can't build a capacitor the size of a billboard? Well, engineers have a secret weapon for this, a little something that super boosts our simple model. It's called a dielectric.
Now, dielectrics sounds super technical, but it's just a fancy name for an electrical insulator. Things like plastic or ceramic or even just paper. But when you slide a piece of the stuff into that gap between the capacitor's plates, something amazing happens. Even though it doesn't conduct electricity itself, it massively boosts the capacitor's ability to store a charge.
And this slide just shows the effect perfectly. On the left, you've got your basic capacitor with just air in the middle, but on the right, we've put in a dielectric. Just look at that. This one simple addition lets the capacitor hold way more charge at the exact same voltage. It's like turning a small water glass into a giant jug without actually changing its size. It's a game changer.
So, great, we've successfully stored our charge. But stored energy isn't very useful until we get it moving, right? So this is where we shift gears from static, stored electricity to the dynamic flow we call electric current. Electric current, which we represent with the letter I, is really just charge on the move. That's it. If our capacitor was a tank full of water, then current is the water flowing out through a pipe when you open the valve. And we measure that flow rate in amperes, or amps for short.
All right, let's pause and clear up something that confuses pretty much everyone at first. For historical reasons going way back, we talk about conventional current flowing from the positive terminal to the negative one. But what's actually moving in the wire? It's the negatively charged electrons, and they are flowing in the complete opposite direction.
This diagram shows it perfectly. See? Engineers draw the arrows for conventional current going one way, from plus to minus, even though we all know the little electrons are physically shuffling along the other way. It's a weird convention that just stuck, but hey, as long as everyone uses the same system, all the math works out just fine.
And here's another fact that might just blow your mind. When you flip a light switch, the light turns on instantly, right? That electrical signal travels at nearly the speed of light. But the individual electrons themselves, they are so slow. They just bounce around randomly on this meandering little journey we call drift velocity, often moving slower than a snail. The light turns on instantly because the electric field pushes all the electrons in the wire at once, like a long tube jam-packed with marble.
So we've got this flow of charge, but how do we control it? How do we decide how much current flows where? For that, we turn to probably the most fundamental rule in all of electronics, Ohm's law.
Okay, that sounds a bit academic, but the idea is super simple. What George Ohm figured out is that current is directly proportional to the potential difference. All that means is if you double the electrical pressure, that's the voltage, you're going to double the flow of current. Simple as that, assuming nothing else changes.
And it all gets boiled down to this one iconic equation. Voltage equals current times resistance.
V equals I times R. With just these three variables, you can describe and design almost any basic electrical circuit. It is the absolute bedrock of electrical engineering. To really make this click, let's go back to our water analogy one more time because it makes it so intuitive. Voltage V is like the water pressure pushing everything along. Current, I, that's the actual flow rate of the water. And resistance, R, is like how narrow the pipe is. A skinny pipe restricts the flow, right? Well, a resistor restricts the current in the exact same way.
Okay, we've talked about conductors that let current flow and insulators or dielectrics that are supposed to stop it. But what happens when you push an insulator too hard? What happens when the dam finally breaks?
Well, that's something called dielectric breakdown. See, every insulator has its limit. If you hit it with a strong enough electric field, basically too much voltage, it will fail. The material that was perfectly blocking the flow of electricity suddenly becomes a conductor, and usually that happens with some pretty dramatic and often destructive results.
This failure can happen in a couple of ways. You can have an avalanche breakdown, where a few stray electrons get knocked loose and start a massive chain reaction. There's thermal breakdown, where the material just gets too hot and literally melts. And then there's defect breakdown, where tiny little cracks or imperfections in the material become the weak points where everything starts to fall apart.
So, from storing charge in a capacitor to controlling its flow with Ohm's law, you can see how these concepts really are the absolute foundation of our electric world. But the story is far from over. As scientists and engineers create brand new materials with these incredible dielectric and conductive properties, it makes you wonder, right? How will these fundamental principles let us build the next wave of technology? What comes next?